Hi, Professor. We are Group 40. We are continuing the second part of the paper using programming slicing to simplify testing. And my group mates are Siva Prasanna Kumar Reddy, it's me, and Karla Venkata Ajay, and Nallapuneni Avinash, Kakani Vishwanath, and Konaparthi Srinivas Teja. And I'm continuing with meaning preservation transformations, like the second part. Meaning preserving transformations continues with the slicing, slicing creates rather a larger slice, partly because T has a propensity to create repetitious code, and partly because slicing is restricted to command deletion. T is like variable here, and to mention an example of a redundant code created by T occurs with the statements like a of I equal to a of I plus 1. We have created a loop here which generates two range checks for the variable I, where only one is required in actual. As an example of the restrictiveness of a command deletion in program slicing, let us consider the program fragment as mentioned in the below. Let us initiate with a variable x and assign a value 1, and then another variable y assigning expression x plus 1, and then z equal to 2 into y plus x. So if the program is sliced with respect to the final value of the variable z, then no lines can be deleted in actual, because every statement of the program fragment contributes to the final value of the z. Like to solve the final variable, the top two variables were created, and the final variable expression contains the about two expressions which gives the final result. However, the simplest program fragment which produces the same final value for z is to simplify z equal to 5. It would actually be possible to elaborate considerably upon the transformations T, but the more complex T becomes, the more likely it is that an erroneous transformation step will be introduced, as rather than the tinker with the definition. So simple meaning of a preserving transformation shall be applied to the program produced by the T. As we have seen before, are small expressions, each of the each of which may be easily verified, but which in combination can yield significantly slice simplification, as shown in the following programs. Some of these transformations are listed in the figure 5 to see how they can, figure 5 in the paper, to see how they can be applied to a slice. Consider the following fragment as shown in the below, taken from the body of the second loop in the step 3. Consider a robust variable, and that was and the expression was assigned to the expression robust, and I greater than or equal to 0 and I less than or equal to max was assigned to the robust. When we solve this expression will be solving in parallel. The x variable was assigned to source of I, and then this I in the array equal to I plus 1, and then the expression robust equal to robust and x greater than or equal to 0 and x less than or equal to 127, and this will be solved in loop with considering the variable x in an array. That was result of x equal to result of x plus 1. And after this, we apply push assignment rule 2 twice to the assignment statement. The rule 2 was mentioned in the coming slides. Was assigned to the statement I equal to I plus 1. Electively moves to this assignment forward two statement positions, as the two statements passed by the I equal to I plus 1, which was array, do not reference I. No substitution occurs here. Thus the program obtained as a below. Applying push statement twice to the statement x equal to source of I, which was array again, entails the substitution of the expression source of I for x in each statement as it was passed. Thus, the program below is obtained from the following procedure, like robust equal to robust and I greater than or equal to 0 and I less than or equal to max. So then the robust variable comes with a new expression like robust and source of I greater than or equal to 0 and source of I less than or equal to 0. There will be an operation occurs between robust, which previous robust variable and the previous robust variable and the current statements. Like this will be assigned to the next statement, that was robust equal to robust and source of I greater than or equal to 0 and source of I less than or equal to 127. And then x equal to source of I equal to 1 plus 1. This I will be incremented in an array. And then result of x equal to result of x plus 1, which was like a new array. The loop will be continued, and applying unfold assignment, which was rule 3 to the first two statements mentioned in the above, and then again to the first two statements of the resulting code fragment, has the effect of collecting together the effects of first three assignments to the robust, will produce the actual result mentioned in the below, like robust equal to robust and I greater than or equal to 0 and I less than or equal to max, and source of I greater than or equal to 0 and source of I less than or equal to 127, and source of I greater than or equal to 0 and source of I less than or equal to 0. The whole expression will be solved and will be assigned to the robust variable. And then comes the x variable, which was source of I. I is an increment statement, which is I equal to I plus 1. And then the result will be created for each array, which is result of x equal to result of x plus 1. And then having coalesced the assignments to the variable robust, the idempotency axiom will be created, and then it can be applied to simplify the Boolean expression giving the robust and robust. The same statement will be created. So the x equal to source of I is and then I equal to I plus 1, result of x equal to result of x plus 1. And then after clearly a method for deciding when to stop applying axioms such as the commutativity axiom is required to prevent non-termination. One way of addressing this issue is to use normal forms for programming language expression, an approach borrowed from the study of computer algebra. Using the transformations in this way, we obtain the simplified version of the conventional slice below. Now we assign 1 to the robust, and we read a source variable, and then we initiate I equal to 1. Then we use while loop till it gets 128, and then the expression is assigned to the robust variable, and result of I equal to 0. The loop increment will be occurred such as I equal to I plus 1, and then we initiate assign I equal to 0 and the robust equal to robust, and I greater than or equal to 0 and I less than or equal to max. This whole expression will be again assigned to the while loop, such as a while of a source of I not equal to null variable, And in the while loop, we assign an expression robust and I greater than or equal to 0 and I less than or equal to max, and source of I greater than or equal to 0 and source of I less than or equal to 127 to the robust variable. And then x variable is assigned to the source of I, and the result will be created in an array. And then we create two variables bc and sc, and we assign some values to each as mentioned. And then we have taken another while loop which until it makes 127. And then we have created an expression, and again we have taken a while loop in which it has to reach until z variable, and then we have to the loop will be continued. And so the next part of the presentation will be continued by other teammate Ajay.